Guys, you're most welcome. Our topic is physical quantities and the SI units. A physical quantity is a feature measured, such as length, force, mass, time, and others. There are very many to mention but a few. We also have acceleration. All those ones are physical quantities. So they are most of the terminologies that we use in physics. And a physical quantity is characterized by a magnitude, size, and a unit. So if a quantity has, for example, a magnitude and a unit, like we have a magnitude and a unit, that's a physical quantity. Like for example, 100 seconds, so that is time. 100 is magnitude, and then magnitude of a numerical value, and the and seconds is a unit, and 27.5 centimeters. 27.5 is a numerical value, a magnitude of a numerical value, and the centimeters is a unit of which physical quantity? That's length. Yeah. So we have SI units of quantities. SI stands for System International, the agreed upon unit for a particular quantity. Like for example, we have mass with kilograms. So mass is measured in kilograms. We have length in meters, like that. We have force in newtons, like that. However, these quantities are classified as base quantities and derived quantities. The base quantities have base units, and derived quantities have derived units and base units. We shall know why. The base quantities, they are those quantities that can only be measured. They can only be measured. They don't have formulas. They can't be expressed as products and quotients of other quantities. For them, they are like foundations of all other quantities. And there are only 7, which is mass, length, time, thermodynamic temperature, electric current, amount of substance, luminous intensity. The order doesn't matter. So their corresponding units are called base units. That is, in a respective order: kilogram, meters, seconds, Kelvin, ampere, moles, and candela. And of course symbols, like I will show you even symbols, exactly, the symbols we have them. So those ones, they are called base units. So meaning we shall have even SI units of derived quantities can be expressed as quotients and products of base units. Why? Because a derived quantity can be expressed as a product or quotient of base quantities. So meaning even units can also be expressed as product and quotients of base units, like that. So for them, they have formulas. Those ones are many. To mention but a few, we have force. Force is equal to ma. Already mass is our base unit. Acceleration is a derived quantity that is expressed as a quotient of change in velocity over time. Time is a base quantity already. Velocity is a derived quantity that is expressed as displacement over time. Or basically, speed is also a derived quantity, which is total distance over total time taken. So like that. So we dig down, we simplify derived quantity up to only quotients and products of what? Of base quantities. Yeah, like that. So these are the ones I've been talking about in the table. These are the base quantities. This table is a table of base quantities. It's a table of base quantities, and then the symbols are there, the respective symbols of units. So now there are some values they estimate for the base quantities. These base quantities like mass, length, and time. These ones are standard values that you may not to memorize. You may not memorize them. You may not need to memorize them. Yeah, like for example, the mass of the sun, like that. Like you don't need to memorize, but they're actually showing you that we have some standard magnitudes of these base quantities, like a particular distance from London to Paris, length of a car, so like the diameter of a hair, wavelength, speed of light, wavelength of light, like that. So they are saying every quantity has just one unit, and a unit can have multiples and submultiples. That is to cater for large or smaller values. So we use prefixes to denote multiples and submultiples of units. I mean of units. Like for example, we can have 1000 meters as kilometer, like as in 1000 can be represented by a kilo. Like instead of writing 2000, you write 2 kilometers. Instead of writing 1 million newtons, you write 1 meganewtons, like that. Instead of writing 5 out of 1000 meters, you write 5 millimeters. Instead of writing 8 out of 100 meters, you write 8 centimeters. So like that. We have these prefixes in a table here, table 1.5 here, this one, of which the order doesn't matter, but what matters is knowing the symbol and the corresponding multiplying factor, because that is what matters. Tera is exponent 12, so meaning terabyte is something related to this. Teranewtons, so like that. Teranewtons, it will be 1 teranewton is equal to 1 times 10 to power 12 newtons. Giga, capital G with exponent 9, mega exponent 6, million, kilo is 1000, deci is 1/10th, centi is 100th of a unit, centi, that's milli, is 1/1000th of a meter, micro is 1 millionth of a unit. So like that. Nano is exponent -9 and pico is exponent -12. And then we need to know how to convert units for some values, like from this unit to this unit, that is from, maybe let me say, smaller units to bigger units. So the trick is simple. We need to know that when we are converting from bigger units to smaller units, we multiply by the multiplying factor. Yeah, but when we are converting from a bigger unit to a smaller unit, from a smaller unit to a bigger unit, we divide by a suitable factor. So now, if specifically we look at length, like we know length, the most common conversions, we have millimeters to meters, or the vice versa, and centimeters to meters, or the vice versa. How about if we bring in areas and volumes? How do we convert them? Remember, there is no that perfect conversion factor for areas and volumes, but we get them from the conversion factors we know for length. For example, 1 millimeter is equal to 1/1000th of a meter. Like 1 millimeter is equal to 1 out of 1000 meters. That is to say, 1 meter is 1000 millimeters. But when you're converting from, what about when you're converting units for areas? It means you have to square either sides to make them areas like squares. So 1 square millimeter will be 1 out of 1 million square meters. Even for volume, that is the same thing. We cube either sides, so we shall have 1 cubic meter equivalent to 100. Is it that? 1000 million millimeters. I don't know. It makes sense. So it will be 1 cubic meter equivalent to exponent 9. Like, let me just say it in exponent. 1 cubic meter will be exponent 9 millimeters cubed. That's the same case with the centimeter. 1 centimeter is 1 out of 100 meters, or basically we say 1 meter is equal to 100 centimeters. Yeah, but that one is easy. We've seen it a lot on meter rules, because 100 centimeter meter rule is 1 meter rule. The other long rule we use in labs, that one is tangible. At least we've seen that. So still, if you're converting length, areas and volumes in centimeters, basically we do the same thing like what I've explained for millimeters. Yeah, we square and cube either sides to get the corresponding conversion factors. So like that. There's a question down here. Calculate the number of micrograms in 1.0 milligram. Here what we need to do is simple. Here is simple. We know 1 gram will be 1000 milligrams and 1 gram will be 1 million micrograms. Like that. 1 gram is exponent 3 milligrams and 1 gram will be exponent 6 micrograms. So now we equate the two because the right hand sides are all equal to 1 gram. So when we equate them, we divide it through by exponent 3 to get 1 milligram in micrograms. And that is the answer. 1 milligram is 1000 micrograms, like that. So you can try out these questions, these ones. Yeah, you can try out those questions. By the way, when you're converting area, you can convert. It depends. Like for example, this question 1, they are saying calculate the area in square centimeters of the top of a table with the sides of 1.2 and 0.9 meters. So it's a rectangular table where the dimensions are given in what? In meters. Now if you are to convert this, you can, there are two ways. You can either first convert the dimensions direct, like 1.2 meters to centimeters and then 0.9 to centimeters. So we shall have 120 centimeters times 900. Yeah, if you multiply by 100 because 1 meter is 100 centimeters. So 1.2 will be 120 and 0.9 will be 90. So 120 times 90 So you get your area in centimeters squared. Or you can first multiply them. 1.2 times 0.9 direct. The answer you get, then you convert it. You convert it to what? To centimeters squared. That's where you multiply it by because every meter is 100 centimeters. So meaning 1 square meter will be equal to 10,000 square centimeters. So obviously the answer you get after multiplying the dimensions in meters, you multiply it with 10,000, you get here to convert to centimeters. So like that. There are even others. So that is it. You try out these questions from question 2 up to question 6. Okay, we have this one, order of magnitude of quantities. So sometimes there is an ability that one needs to acquire. So a physicist must possess the ability to estimate orders of magnitudes. Yes, because they help sometimes in practicals. Yeah, in planning and analysis, when we are carrying out what experiments in labs for, let me say, A-level sections. So you can be able to estimate, like, let me say, the mass of a car, life expectancy of a human, like that. We need to estimate values, and sometimes it can be a question in paper 1 AS exam. Yeah, it is possible. There's a video I uploaded about the assessment, how papers are set. You go to my playlist and see, and you will see that video. But there's a question that comes from the estimation of orders of magnitudes. They can bring a question and they say X is what is the estimated value of the volume of your head. It is possible. Yeah, it is possible. They say estimated the diameter of your hair. Can you imagine? So like that. We need to be able to estimate values, magnitudes. Hey, like that. Like they're saying, the approximate values of common objects or physical quantities should be known. Like a carton of orange juice has a volume of 1 liter. Yeah. The mass of a large car is about 2,000 kilograms. An adult has a mass of about 100 kilograms. Yeah, those huge ones. I'm below that. Okay, like that. So if you know an average mass of an adult person, then it means you can estimate the mass of an elephant, because how many adults can make up an elephant? So like that, I think you can estimate the number of human beings that can make up an elephant, and then you'll be like, let me multiply 100, that's the mass of a human, of an adult, by a particular factor E, and then you get the mass. That's estimation. So for estimating values like the mass of a plane, an Airbus, there's no okay, like that perfect value. Like it means if it's an examination, they will give a range of values that if your answer is within the range, then you get a mark. Because I don't think you can be okay, the whole class, entire class can estimate that same exact value unless it is standard. Like for example, speed of light in air. They say estimate the speed of light in air. Obviously, that one we know. It is 3 exponent 8 meters per second. So if everyone says okay, rates say that, obviously it is correct because that's the one that is known and agreed upon. Yeah. So you try out these questions. Estimate it one significant figure the following quantities. This one, they are here. The mass of an orange in grams. So you try out these questions here. Okay, this question, but these parts here from A to K. Yeah, and you see. So in any case, like if you want, you can use Google, you can Google them, you can use whatever platform you want to estimate. Yeah, like that. And if you can give me the feedback in the comment section, there's no problem. Or in case of any question, still you can comment, like can write to me in the comment section. So like I told you, this is another classification, derived units. This one, derived units, where they consist base quantities, that is derived quantities. They are, let me say, products and quotients of base quantities, or even okay, or maybe they can be products and quotients of, let me say, base quantities and derived quantities combined. Because like for example, force is equal to ma, where mass is a base quantity and acceleration is what, is a derived quantity. So like that. These ones have formulas. However much we can have some derived quantities with the instruments. Like for example, weight. Weight is a weighing scale that is calculated in newtons to be directed what, values in what, in newtons. So like that. So derived units consist of some combination of the base units. Yeah. So the base units may be multiplied together or divided by one another, but never added or subtracted. So yeah, like that. It is obvious. You never get a unit that is, like for example, kilograms plus seconds, and that one's not there because you can't add different units together. You can't subtract different units together, like force minus momentum. Impossible. You can't. So I have some examples of derived quantities and their corresponding units, like unit and then derived unit, the one in base quantity form. So in the table 1.6, we have hertz, meters per second squared. Like of course the corresponding quantities are this side. The first column here, frequency, hertz, or it can be per second. Remember, frequency is 1 over period, so it is per second in that way. Velocity is meters per second, and the derived unit in base quantities, still it is meters per second, because velocity is like length over time. Acceleration is meters per square second, because acceleration is like the second derivative for like length. Yeah, force, Newton. That's the unit, like SI unit. But the base units, we have kilograms, meters per second squared, because it is MA. Momentum, it is Newton second. Or it can be kilograms meters per second. Why? Because momentum is mass times velocity. Energy is joules, or it can be kilograms meters squared per second squared. Why? Because energy is like force times distance, like work done, work just. Power is watt, has a unit. SI unit is watt, and derived unit is kilogram meter squared per second cubed, because power is energy out of time. Electric charge is coulomb, yeah, and the derived unit is ampere second. Why? Because a coulomb, a charge is current times time. Potential difference has unit volts, and the derived unit is kilogram meter squared per second cubed per ampere, because potential difference is work done per unit charge. Electrical resistance is ohm, or this one, kilogram meter squared per second cubed per ampere squared. Why? Because electrical resistance is what? Is potential difference out of current. So basically that is it. These are some of the examples of derived units here in this column here. So if they say what are the base units of speed, obviously it will be speed. We need, by the way, the critical part of this, the tricky part of this is knowing a formula. If you can, for example, trace the formula of a derived quantity back to the what? Down. Okay, you trace the formula of a derived quantity on the right hand side down to only and only quotients or products of base quantities, then you can derive. Like for example, speed is easy. This is just one step. Speed is total distance over time. Distance is a base quantity because it's basically length, and then time is also a base quantity, so it's quotient of what? Distance and time, which is meter per second. But we have some bulky ones, like for example this. No, even this one's easy, but we need to get volume first, because volume, like for example, if we use a cuboid, yeah, because that is volume. You just get a particular shape. For as long as you're defining volume, it will be length times width times height, where if you are to get now the derived unity for volume, it will be meter, width is meter, and then height is meter. Those are all lengths, which is meter cubed. So getting density, derived units for density, it will be kilogram over cubic meter, period, which is kilogram per meter cube, period, like that. Then for pressure, we have to trace down force over area back to what? Still back to only quotients and products of these quantities. So it is like that. So we have some applications of this. This dimension analysis we are looking at, we use it to check whether equations are, units of the equations are balanced. Like, for example, if you see pressure and then is equal to force over area, are units balanced? So if they are balanced on the left and right of all the terms, involved in the equation, then it means the equation is homogeneous. So we use the dimension analysis to check the homogeneity of an equation. Homogeneity of what? Of an equation. Which also affirms the fact that if the equation is homogeneous, it can be correct, it can be valid. Yeah, like that. But not all valid, not all correct equations are valid, because we can have an equation that it is homogeneous but it's not valid. Yeah, we shall see those examples as we are going. Like the example is here. We have this first equation of motion in a straight line. Velocity is equal to u plus at. So we can prove whether this equation is homogeneous. If you look at this, there are three terms of this equation. We have velocity. Velocity has units, derived units, meters per second. So this term on the left is meters per second, is equal to meters per second for initial velocity, because this is final velocity here. This is initial velocity, is equal to initial velocity plus acceleration times time. So when you simplify acceleration times time, this one, which is meters per square second times second, we get what? We get here meters per second. So obviously you see every term in the equation, this term is in meters per second, this one meters per second, this one meters per second. So equation is homogeneous, the units are balanced throughout. So we say in any equation where each term has the same base units, the equation is said to be what? Homogeneous or balanced. So it is also correct, yeah, because we know that equation. So that's the application. So I beg to stop here. In case of any questions, guys, you comment on this video. We can look for each other for more clarification on other platforms like WhatsApp. Yeah. So thank you. We meet again. Please subscribe and like for more content. Thank you. God bless you.